just a very quick note. There's a question on the forums about something I posted the other day. What was the thing I was posting? It was about getting pointers to typed variables and typed arrays, which is actually something that you can't really do in PB as it stands. And it's because there's a change in the way the syntax was handled at some point. All of a sudden you can't do it anymore, and I never noticed. So the question was, Steve's asked a question about, can you make a video about what you were explaining? I sort of get what actual issue is focusing on, but about a typo. Kiss was meant to be list. I had no idea what he was talking about when he said this, or what you're talking about. Can you explain how variables, arrays, and types are created and stored in memory? More visual explanation of what is happening. We'll try and do an overlay of that in a second, I guess. I've always been interested in how memory works and how the data is stored and accessed in data. Well, below I've posted an elaborate example that shows exactly how this stuff is done. It's a simulation of how it's done in PB. And we'll go through it in a second, actually. I have an idea about types. Is there any reason why you can't create a type and have it set up in memory side by side, similar to an array, instead of creating a type cell as you need it? No, there's not. What you're describing there is something called an array of structures. We use an array of pointers. So when we have things like a typed array or a list or whatever, the data itself can actually sit in memory side by side in certain versions of PB. I think in the current version it doesn't, but in old versions of effects this was tried out. But okay, beyond the point here. The reason why we actually have the handle separate the system here to separate these things is because we wanted to support inheritance, and it does support inheritance. That means that you can actually have a base type, let's say you're making characters for your game. You have a base character type, and that has all the simple features. So the simple fields that all types are going to have, like it's going to have a location, a sprite, a status, what kind of score value it has. If we're talking about a game, anyway. And then what we would do later on is when we want more fields than that, we want very particular data that only is related to a particular type of character in our game. So let's say we're making a platform game. I've got a few characters there. I've got a large monster character, a dragon character, or whatever. They all might have different attributes, things that are needed beyond the same handful of basic fields. So we have different structures for those things. So what we can do with PB is they're all inherited from this base structure. We can create them in the same array and iterate through that array as if they're all the same. We can't do that if all the data is packed together in memory. That doesn't work, because we're assuming then if we're all packed in memory that every type is the same size. Obviously, if we're having a base type and then we're extending that type by adding more fields to certain types and not others, they'll all be different sizes. So it's not that it's not impossible. Okay, it is possible, but it's not as nice and comfortable to do. Anyway, so get down to the next part here. The difference between the array polygon 9.2 creates an entire array in memory that you treat like a second element and mimics the type. Let's say, yep, and dim polygon 3 is poly. You can create. Well, that's true. When you create a two-dimensional array, as we've outlined here, we are creating one giant block of memory, and the indexes here are used to compute where the individual piece of data we are interested in is every time. So there's a multiplication that occurs inside here, and there's two clips that occur to check these two fields are within a certain range. We have to clip them, we have to do those things at runtime because we don't know what this range is going to be. We don't know the size of the array. It's never actually stored. That's a different idea than what we have. We have dynamic arrays. Languages like C, for example, they just have these kind of literally declared sized. So we go, hey, give me an array that's 100 bytes in size, and once it's declared, that's it. You can't touch it. You can't delete it. You can't resize it. Whatever. Often that's quite useful. Often it's quite a hindrance as well. So they both have a usage, a best practice. In other words, there's times where I would use one and not the other. Times I would use the opposite. Right. So here we're going on. This is the equivalent. Yeah. So here Steve's saying that this here is the equivalent of going polygon here. So if the type is just variables and the type array size, then why can't it be something very like standard array is? They using the same data and the same size, and the type knows are the numeric values being used. This is one of those things that was tagged in one of the design docs, right? So that we've got these different ideas about different kinds of arrays. Like you could actually have what's a hash map or array as well, or like a keyword array. So you use a string as the index, and it computes where this key is within the structure itself, which is really handy for doing properties. And if you've ever done any PHP or something like that, you toyed with this kind of programming. It has a great use case, but there's detriments to how if you're using a string that has to compute a hash, and computing hashes is not a straightforward thing. It takes time to do that. Having an array that's stored as one big chunk of data and then indexed like that is not a bad idea. In fact, it's one of those things that we'll probably end up having in PB at some point. We already have a thing in PB that we call static. We probably should call it an embedded array. So if you do type, I don't know, since we're talking about game characters, my game, we'll call it object actually. My game object, this would be the base object or whatever. And type, oh jeez. I think we have a status field or something like that, and we have a status field. We have its coordinates on the screen, and we might have a list of what children can be attached to this parent. So we might have an array like this, child, and we have a maximum of, let's say, 20. If I dimension, we'll just call this thing A as my game object. A equals new. So this is the declaration. So we're adding this to the variable table during the compilation process. There is a runtime element too. This actually generates the allocation of A's parent structure, and to fill the actual data structure in, we need to do a new. It can just be done when you do a write to it, but using new is a better way. It's a more normal approach these days. Okay, so now we've got A has this data here in it. We'll just check to show you what I'm talking about. Go to variables, hit here, and we have, you'll notice something interesting. We've got our integer field, our XY field, and our child array is now effectively, these are separate fields that we're indexing like they're an array. This is what Steve's talking about. These are just sitting in memory as a field inside here. If we want to have a second one, I don't know why, child 2 or something like that, we run again. If we look at the structure, we'll see that they're just sitting side by side. technically, if I wrote to child 1 and used index 21, I'd be writing to this field here. And if you don't believe me, a dot child 21 equals 1000. So we've got a second array after the first array, and we should get this where we hope. It thinks it's in child 1. Now this happens because when we write to this field, an array field within a structure, we have none of the protections of a normal array. What PB is doing is going, give me a pointer to this thing, this parent-child field, wherever this happens to be in memory, and then we're just taking this index and multiplying it by the size of the index. In this case, these data elements are the integers, so they're 4 bytes apart. So it's effectively going, we could try and poke that there as well. We get a pointer to this. We could go a dot child. Well, that phrase. Oops, sorry, I didn't want to save that. Here. Hasn't given us a pointer to that. Oh no, it's not, sorry. It's not a subtype, so we can't do that. What I could do here is to really blow your mind, I guess. I can wrap this in a type name. I could go my array, put child in here. Oh, sorry. Child is my array. It's a convoluted way of saying this, the exact same thing. So it's going to insert this array of 20 elements here, but keep them the name. So we could go child dot my array to return the pointer to it. Syntax error. What have we done? Oh, sorry, we can't do that anymore. Now it's child dot array 21 to get to that same field. Back to console. Here, stop, thank you. Pointer, yeah, it's giving us a pointer over there. I think it does work for arrays there as well. I can't remember if that's hooked up or not. Child 2, let's have a look. No, oh sorry. That is returning a pointer, so we have to wrap that as an integer to print it, because print doesn't understand pointers. It does, yeah, sorry. Bit of a convoluted way of going about that thing. So what I could do is I could grab the pointer here to demonstrate we're doing the same thing. If I write this into value 20, this should be at the end of this child embedded array here. It's an embedded array because it has no handle. It's literally just a segment of memory that's laid out and written to and read and written to in this particular pattern. In this case, the pattern is integers. We can't have types with this kind of approach, but that's more of a lacking of how the phraser works, because the phraser is very old, and you're getting back to that stuff again. So if I wanted to do a poke int, I would have this pointer, I would have 21. This is going to be the value, effectively, the first index of here, this child 2 array. Multiply that by 4, because we're talking about an array of integers, so each field is 4 bytes in size. And I want to poke this thing with, I don't know, 5555. So when we run it, up to variables, have a look at it, and in child 2 we have 5555. I think I've got off topic here. This is pretty much what Steve's talking about. We can have arrays like this. Now, our limitation here is how the phraser actually works in PB. The phrasing code's old, and it does a thing in it that doesn't allow for nested types. What we ended up doing to avoid some of this kind of you can kind of roll your own array of structures in memory yourself by using typed pointers, and it's really the same thing. I'll use a different structure this time. Go new. It's very windy and very rainy outside tonight, so we use the vertex. Oh, sorry, we'll go back to 3. We'll give this thing, 3 basic fields, X, Y, and Z. There's a floats this time. If I allocate a bank, if I just go, we'll call it vertex bank, new bank, and it's the size of vector 3, and I store 1,000 coordinates in it, multiplied by 1,000. That gives us a safely allocated chunk of memory that is the equivalent of an array conceptually. Now, if I went to dim, we'll call we'll just call it vertex. Okay, 1,000 as vector 3. We've really got an emulation of this, but as Steve was talking about before, this time this here is the equivalent of having all of that memory sitting side by side. The only downside is that you can't have a convenient index of it. If I run through, I go, for loop to 1,000, go to 999, next, vertex, vertex loop, dot x equals blah, blah, blah. We run through and set up the values for each vector. Now in memory, these 3 fields here that are in the vectors, they are not necessarily sitting next to each other at all. In fact, they're in different locations all the time. This one here, our emulation of that would be, but we're going to do something a bit different. So we would go for here 9 to whatever that was. It's our loop through. This time we need a pointer. Call it me or something like that. I don't know. Was it vector 3? Vector 3 pointer. So up front, I'll do it the longhand way. We'll go me equals get bank pointer, vertex bank. So we get the actual address, the way this bank exists in memory. There's a bracket missing there, and then we add on loop times the size of vector 3. What we're doing there is we're getting the address of this. We're doing the equivalent of what this here does. Once we have this, we can go me.x equals whatever that was. We can set the 3 fields any way we like. X, Y, Z. I'll set the same thing. So we can fill that memory. Now what we're missing in PB is an array index support from these pointer fields. What we need to do this to be more comfortable for people is actually something like along the lines of this. So we still need to grab the pointer to make sure, and at the end of the day, you're responsible for making this stuff not point at stuff that you don't own. If I delete this bank here and if I try and grab a pointer to it and try and write into memory, your program's going to crash. If you write outside the bank, you're going to crash. If this index is illegal, you're going to crash here. I cannot protect you from that. That's part of the reason why arrays work the way they do. They have to be safe. Because people do weird stuff. Not that it's bad. So if we had index support from here, what I'd be able to do, or what you'd be able to do, is do this. It would just look like a normal array. It's a lot cleaner, it's a lot more convenient for people, and I'd have no problem with that at all. And in fact, it's meant to be supported. You know, don't shoot me, it's not. It's meant to be supported. You got to remember that it's doing the same thing, right? It grabs the me base pointer, this address in memory, takes loop, multiplies it by the size of your vector 3 structure, adds the two things together, adds the offset field here, and then pokes this value into memory. So there's a bunch of stuff that happens anyway. We're getting past some things, but not everything. If you look at this version here, what we're actually doing is still slower than what this would be. If we just did this, now we have one basic offset, and we just add me equals int me plus size of whatever it was, vector 3, was it? Vector 3. These size ofs here, they resolve at compile time. It just works out how many bytes, what the integer value of this thing you're asking it to get the size of. So something that's got 3 float fields in it will be 12 bytes. Right. The int here will get resolved as well. It just returns to a straight addition. Now this is better. The reason why this is better actually is you don't have multiplications every time you write or read from the field. These can't be clipped. If I added clipping to these things, you'd have to have like a structure like we declared in this other example back here. It was over here somewhere. Yeah. These don't have clipping as well because it has no idea, as you just saw before, it has no idea how big this array is at runtime. Not a clue. I can hard code output code to check the size to the indexes, but it's more bloat for nothing really. Alright, so this is something that we should look at doing. You know, this is a decent idea. There's nothing wrong with this. So this would be the best way if you're desperately after high performance and you're desperately wanting to do things like have translations out to machine code. You know, in the runtime, there's going to be benefit, and the type caching stuff actually does this for you internally. Basically what type caching does is it turns this original expression up here into almost this. It's just not implemented in 165. And the step up from 164, the earlier versions of 164 to the final one that have caching implemented on those bits of code that it can actually understand and cache well, is multiples of 3 or 4 times as the speed, just because it's safely worked out that it doesn't need to keep checking if a bank exists or the indexes you're using are legal, because you're using the same index in the same array multiple times, one after each other. Wow. I don't know if this is very useful or not. I have no idea. I'm not going to worry about cutting this together or into anything. So getting back to what Steve's talking about, this is not a bad idea. It's actually a good idea and has its place. But if we only had arrays that worked like this, then you'd be going, gee, why can't I resize my array? Why can't I pass my array into functions? All of these secondary benefits that we have, right, that allow us to do stuff that have detrimental impacts like okay, it's a bit slower to read from a field. And it's slower because we're trying to be safe about it. if I didn't care about, catching crashes and catching runtime errors, and can run quicker, but that's not very useful when something goes wrong. The bigger your code base gets, you need those things to trip errors reliably for you. I know error detection can be a bit of a problem in PB. It's easier said than done sometimes. Anyway, so I put together this big example down the bottom here. Went off on a tangent. I've got this program over here. I'll post all this stuff to the thread anyway. Alright, this massive bit of code here simulates how we would... It's a simulation of what PB does to programs, what we type in and what happens to it after your hands have left it, and the compiler breaks all of these... Anything that's a variable, an array, or a name, first of all, gets put into a global heap. Here I've just called this thing a variable heap. It's just an array, and it's an integer array in this case, but internally it's just a chunk of memory, basically. Here I'm using an example, we've got a variable called A, a variable called B, C, an integer array called table, and a typed array called bad guys. Now, all of these things, if they were discovered one after the other, this is how they would be in that table. There would be, the compiler takes the variable name or the array name and converts it to this global variable index, which is just a position on this heap. Here, these are just indexes. I've just set this to 1,000 possible variables. Below here, we've got a simulation of some example code of what you would have typed in, and this is what the runtime is doing. So the variable A gets understood as this is index A up here, which is offset 1. So we're storing 45 in this location in the variable heap. We're storing D in the variable heap, variable D there, which is 1,000. D is offset 4. This is the equivalent of this code here. We're adding A and B together and storing them in C, so it's just like doing normal integer array operations. Showing the result here. If I run this, we'll see what's actually happening. So a variable test, we've got the result 1,045. Back here, variable A is 45, variable D is 1,000, and the result stored in C, so that seems to be correct. To make an array, we've got a simulation of an array called table and its size to 100 units. Same thing, this table gets its own unique index on the heap, and every time that you talk about table, we're reading the heap to get the handle. The handle in this case, when we dimension something, whereas the simulation, there it is. So when we do dim table, the phrase is taking the array name, putting it into a list, coming and giving us back what global index is going to be, which is this variable index thing here. Once we have that, every time it sees table come up in the program, it inserts this particular index into that structure, or into that this array call in this example here. If we have a look at the dim array, we're checking, is the size legal? Do you have something already allocated? Are you empty, in other words? If you are, we should delete the data inside that. I think I've mentioned this stuff before in other examples. Like a lot of the scripting stuff we've been talking about lately does exactly the same stuff. Here I'm using a bank. Now, since this array is integers, each integer is 4 bytes in size, so we compute the amount of memory by taking the size we requested in indexes and multiplying it by 4. Gives us a handle to this particular bank that we'll use later to store data, to read-write the data to the array. So we store this for later use. Go back up the top here. That's our simulation of dim. We have a write integer function, which does the same basic thing. It looks at the array name, index, checks if there's, reads the handle to check, has this array been dimensioned? Does it have any data at all? If it does, cool, we check the index. When we check the index is bigger than 0, check that the index is it less than the size of this bank. In this case, we're using banks in PB. And if that's true, we allow it to poke an integer into memory as if it was a normal PB array. Here we've got some extra code there where if these things here fail, we can throw an error, etc. So now reading array is the exact same bit of code, except we're peeking from that bit of memory and returning it back to the person, back to the code back here. And that's how an array works. A type is a bit different. A type we basically have an integer array. Rather than we store integer data in the array, we're storing handles of types in the array. So the analogy I made earlier today was that variables are like the ground, arrays are like the tree trunks, and types are like the branches of the tree. So to simulate this dim bad guys as character, we're just calling this dim 1D array thing, which our compiler would have given us a unique index identifier for this bad guys array. So we never clash with anything else, of course. They always sit in the same variable heap down here. We have a look at the function briefly. I know this is kind of going, I'm skipping through this pretty quickly, but it's alright. Oh, find declaration. So to mention the array, we're checking this handle for pre-existing data. If it has something, we should undim it, of course. I didn't bother. Then we go ahead and allocate a bank to represent the array, and then we store this handle for future use, so when we access the array later on. Go back to the top. Add dimension. So to allocate a type for this position here, what we're doing is we're allocating another block of data that represents this character structure. So this variable here is what this size of here is what our size of would compute for us. So this structure at the top here is an example of our character. We've got our five fields, yeah. And these fields get turned into just numeric offsets. Field X becomes offset 0 because it's first. Y is 4 bytes ahead of that. These are all in bytes, not in integers, by the way. This is how many bytes where this thing is stored, structured in memory. And these are all offsets from the pointer to this first thing here. So X is where the pointer is. It's the data right at that location. Y is the data 4 bytes past that location. Size is 8 bytes past that location. Sprite is 12. Score is 16. And then we have a type here a constant representing the size of this structure in memory. We need that for when we do this allocation of types, and we actually need it for when we delete types as well. But here I haven't bothered with delete. I've just done an allocate. So this line of code here, we've got a normal array writing of something into the array, which works pretty much the same as an integer does, except we're storing a handle and not an integer. That's a conceptual reference. It's just an integer value we're storing into a chunk of memory in somewhere in memory, but we're just treating it as if it's special. That's the only difference. So find declaration. This allocation here is literally just we're allocating a bank of memory of this size to store our fields and returning it back to us. once we've got the handle, we write this into here. That's a wrapper of what we already had. So we're writing the handle into a 1D array. To do this quickly, it just reads this as if it was an integer array. It goes, oh, give me the old handle. If there was one, we should delete it here, but I haven't bothered. And then we just write the new one in over its place. Now to store data in this thing, so this does the allocation of a new character. This here writes data into the field. Got down the bottom here. We've got our global index of what this array is. We've got the index within the array, and we've got the field offset and the value we want to write. So here we're only supporting integers, so it's all just integer. First thing we do is we read, has this array been dimensioned? If it has, it'll give us a handle of this particular location. So we're reading from this array at this index, getting a handle. If has a handle in it, or is any value other than 0, then it must be a bank handle, because we're using banks here to represent the blocks of data. I'm doing 2 checks here. Is the handle non-zero? Okay. Does the bank actually exist? Okay, good. We check our field offset, which is our offset within the structure, just in case we're passing the wrong field to the wrong type. We don't want to be writing outside of it. Beyond this demo, there's no way I could actually test. And we're checking it to see if field offset's inside this chunk of memory size. If those two pass muster, it just writes it into memory. If they fail, something's wrong. So we've got this extra code here that's more about cleanliness than it is about actually the operation itself. And the read is the same thing. It's exactly the same code, except we're reading from that location and returning that value back to the main program. So here we're doing this line here, we're writing to these fields, X position within the array, it's location 5, this is location 5, location 5. So if we wanted to do something like, if we had a loop down the bottom here, we'll go for 0 to 10. I don't know how big that array was allocated. So we'll just go So we want to write into the bad guys array, make a little comment here, we're going bad guys loop.x equals random, over the screen with this, 800. Make it 600 there. Y 600. So we've got our field here, and we're going random 800, random 600, and we want to we're looping through these indexes. We use loop to go through here. So that's the equivalent code. We run through and initialize those values in this particular type. Now, if we do that straight away, that won't work because we haven't allocated all of these types that we need. So we actually need to grab this. Before we write to this particular bad guy, we've got to allocate a type for him or her or whatever you want to refer to it as. At this position, this is the equivalent of going, bad guy, if that's the right thing. Bad guy is equals new, whatever that was. So we allocate this type for this location within the array, and then at the bottom here we'll render them out. Just the circles or whatever. How creative. Unbelievable. Gee, that tap's starting to annoy me. No more annoying tap. So we'll grab the x coordinate of this thing, the y coordinate, reading from here, grabbing the loop. We'll do a circle here, circle x, y, 30, random RGB, back to here, circle C. And that should be an equivalent of the same thing, pretty much. So this is the going x equals bad guys, was it? Dot x pos. And circle would be the same. Let's try and run it so we haven't killed it. I didn't declare loop, did I? No call loop. Or x or y. That's very... How dare I not do that? X, y. I want it to be filled, thank you. There you have it. Amazing, isn't it? So this simulation pretty much gives you the guts of how PB works. Now, granted it's more complicated than this, but this is the kind of thing that we have to do to get data in and out of things. Now, all in all, what Steve was talking about is a good idea, and it is something that we should actually implement. The ability to grab a pointer to something, or whether it's via pointers or whether it's by an array that is where you have some way of telling this thing you want this to be, you want to override the existing method that it uses with a different method. That still has the index problem. Like if I tell it here, this system here, our system is dealing with the array as it's an array of pointers. So each cell has a pointer to something, the data somewhere else, and then we're working out what this is and then adding the fields onto it, right? As I was kind of kicking through before, if we had a second example here, even if we convert this to an array of structures, I don't know, you could have like an AOS tag or something like that. You probably want to have an array of structures. I mean, something verbose that people could look at and go, oh yeah, I get what this means, or they could go and look it up, because acronyms are death. There's too many acronyms in PB as it is. We still have the same problem, right? Even if this is all one block of memory now, right? If this vertex data here is just a big allocation of 1,000 times the size of this thing here, this what is it, 12 bytes. So 12,000 bytes in memory, all consecutive in one buffer. When we do index all the way through here, we have the same problem. This is computed all the time. It's got to be clipped, computed, etc. It's quicker than what we have before. Yes, definitely. We run into problems where you can't move data between the structures, etc. But that can be solved. That can be solved. All those things can be done. That's something we need to do, really. Another one is actually having an actual static declaration. So if this thing here was declared at compile time, we could get some benefits from doing that, which is a different conversation altogether, actually. At the moment, this declaration works. It goes, this is your name of this particular thing, and you want to store this kind of stuff, this kind of data in this array, but the size and the array itself are not allocated until the program is running. In some cases, you might want to have, dim A It's vector 3 or something like that. And it would do the allocation up front. So the benefit is that this is sitting in memory all the time. The detriment is that you have, if you did want to change it at runtime, you can't. It's probably hard to follow that, but anyway, I hope that gives you some insight of what this question is talking about, and I'll put these things up in the thread with this thing as well. I do want to spend all night on this particular question but yeah, there are different ways of storing arrays. Lots of different ideas about storing this data are useful. I mentioned in the thread itself, up the top here in the video, I'll go through a bunch of things about arrays in particular, like having ranged arrays, for example. It just comes to mind. That would be useful, and very useful actually in many regards. So you can have an array just up here, whatever. You could go dim table, and rather than actually have, you can specify what index range you want. So -100, I don't know, to 200 or to 2000 or something like that. So you can actually refer to this table. You can go table -20 something equals 45. Because sometimes it's more convenient to think like that. You might have a value that's oscillating up or down, that you don't want to think about clipping the value or moving it, offsetting it all the time, and to have the runtime do that task for you it's kind of easier. But again, another feature, another thing that needs to be tested and needs to work in with everything else. We have lots of limitations that are byproducts of how the old Fraser works, and I'm a bit tired of the old Fraser, to be perfectly blunt. Yeah. All right, that'll have to do. Thanks for watching, and see you next time. I'm just going to chuck this up as it is, pretty much. I'm not going to bother editing this at all. Well, not much anyway. See you next time. Thanks.